This video is for Chemistry in the Earth System, Unit 5.2, Solutions. Today's essential question is, how do the components of a solution and the conditions around them affect how substances dissolve and behave in mixtures? Solutions are a fundamental part of the world around us, from the air that we breathe to the fluids that are in our bodies and the beverages that we drink. Solutions play a critical role in sustaining life and enabling many of the processes that we take for granted. When we mix sugar into tea or salt into soup, we are creating a solution, which is a specific type of mixture where substances combine in a uniform way. In this lecture, we'll explore what solutions are and how they behave, the different types that exist, and why understanding them is essential in both science and everyday life. Let's begin by defining a solution. In chemistry, a solution is a homogeneous mixture, meaning that it has the same composition throughout. When a substance is completely dissolved, its particles are distributed evenly at the molecular level. For example, when you dissolve sugar in water, the sugar molecules are surrounded by water molecules and then evenly spread out. If you look under a microscope, you wouldn't be able to distinguish the water from the sugar because they are thoroughly mixed. Importantly, solutions remain stable over time. They don't settle, and the components don't separate. Every solution consists of two key parts, the solute and the solvent. The solute is the substance that is being dissolved, and the solvent is the one doing the dissolving. Think about adding a spoonful of salt to water. The salt is the solute, and the water is the solvent. In most solutions, the solvent is present in a larger amount than the solute. While water is the most familiar solvent because of how well it dissolves a wide range of substances, it's not the only one. Alcohols, oils, and even gases can act as solvents under the right conditions. But solutions aren't just limited to liquids. They can be found in all three states of matter. That's right, solid, liquid, and gas. Solid solutions include alloys like brass, which is a combination of copper and zinc, and steel, which is a combination of iron and carbon. These materials are stronger and more useful because of the way atoms are mixed at the microscopic level. Gaseous solutions, like the air we breathe, are mixtures of gases, which includes nitrogen, oxygen, and other trace gases. Most of the solutions that we encounter in labs and in the home are liquid solutions, such as salt water or vinegar. Regardless of the state, what all solutions have in common is their uniform distribution of particles. Water is also known as the universal solvent because it can dissolve more substances than any other liquid. This amazing ability is due to water's polarity. Now, a water molecule has a slightly negative oxygen end and a slightly positive hydrogen end. These charged regions make it easier for water to interact with other polar molecules or ionic compounds like salt. Water, in this situation, can surround individual ions or molecules, separating them and allowing them to disperse evenly. This process is helped by hydrogen bonding, which occurs when water molecules form temporary bonds with solute particles. These properties are what make water so crucial in chemical reactions, biological processes, and even environmental systems. Now, let's look at how substances behave once they dissolve in water. Now, some compounds break apart into ions when dissolved. These are called electrolytes because they allow the solution to conduct electricity. Strong electrolytes, like table salt, which is NaCl, or hydrochloric acid, which is HCl, fully dissociate into their respective ions. Weak electrolytes only partially dissociate. Then there are non-electrolytes, like sugar or alcohol, which dissolve in water as intact molecules and do not conduct electricity. Electrolytes are essential in many real-world applications. They're what allow your nerves and muscles to function, and they're used in batteries and medical treatments. Now, the amount of solute that can be dissolved in a solvent depends on several factors. Temperature is one of the most important. For solids, increasing the temperature generally increases solubility, but gases are different. They become less soluble as temperature rises. Pressure mainly affects gases. Any higher pressure can force more gas into a liquid, like CO2 into soda. Chemical makeup also matters. There's a rule that goes, like dissolves like, and it means that polar solutes dissolve best in polar solvents, and non-polar substances dissolve best in non-polar solvents. That's why oil and water don't mix. One is polar and the other is not. It's important to distinguish between how much solute can dissolve, which we call solubility, and how fast it dissolves, which we call the rate of dissolution. Even if the total solubility doesn't change, we can make things dissolve faster. Crushing a solid into smaller pieces increases its surface area, giving more space for the solvent to do its dissolving work. Heating up the solvent gives its particles more kinetic energy, which increases their interactions with the solute. Stirring or shaking also helps by moving solvent molecules around and bringing them into contact with more solute particles. Solutions can exist in different saturation states. An unsaturated solution is one that can still dissolve more solute at a given temperature. A saturated solution has reached the maximum amount of solute that it can hold. If you try to add more, it won't dissolve. However, under special conditions, you can create a supersaturated solution. This happens when you dissolve extra solute at a high temperature and then cool it down slowly. The solution remains clear, but it's unstable. Any disturbance, like adding a tiny crystal, can cause the excess solute to rapidly come out of solution, forming what we call a precipitate. Now, carbon dioxide provides a real-world example of gas solubility. When CO2 dissolves in water, it reacts to form carbonic acid, giving soda its tangy flavor. However, as the temperature of soda increases, CO2 becomes less soluble and it escapes in the form of bubbles. That's why warm soda will taste flat. In factories, soda is bottled under high pressure to keep more CO2 dissolved. Now, when you open the bottle or the can, the pressure drops and the gas escapes. This also connects to environmental issues like ocean acidification. As CO2 levels in the atmosphere rise, more dissolves into the oceans, forming carbonic acid and affecting marine life. Solutions are essential in countless real-world applications. In medicine, they allow doctors to administer drugs directly into the bloodstream through IV fluids. In the food industry, soft drinks and sauces are all examples of complex liquid solutions. Industrial processes use solutions to deposit metals into electroplating or clean, very delicate electronics. Detergents, which are also solutions, help remove dirt and oils from surfaces. Environmental scientists use chemical solutions to test water quality and remove pollutants. Understanding how solutions work helps us solve practical problems and improve technology. At this point, you should be able to generate a full and appropriate response to today's essential question. How do the components of a solution and the conditions around them affect how substances dissolve and behave in mixtures?